Hi, welcome back to the lecture series on computer vision from scratch. Today, we'll be learning about transfer learning. If you have not watched some of the previous videos in this lecture series, don't worry because this lecture is almost like a standalone lecture because the concept of transfer learning is universally applicable for various deep learning related problems which are within computer vision and outside of computer vision. And if you have been following some of my previous lectures in this course, maybe you would have felt some pain because we have been trying so hard to build a deep neural network that can classify 5 flowers data set with some decent accuracy, right? We were hoping to get some 90%, 95% accuracy, but none of that happened because we were still trying simpler models. So if you felt that pain by the end of today's lecture, you will feel very, very good because today we are going to have some happy time by building a model that actually performs very good classification on our data set. So with that, let's get into the lecture. And as we always do in this lecture series, before we start the lecture, let's remind ourselves that there is a reason why we have started this computer vision series, right? It's to learn CV techniques and its basic fundamental principles from scratch so that we can use it for our own benefit after the course. So if there is a reason why you have started this, we should finish it. So that is the pledge that we will take together. So ideally, if you're studying this course with one of your friends or acquaintances, feel free to keep each other's accountable to make sure that you are finishing the lectures one after the other. And if you would like to keep yourself accountable by publicly commenting, feel free to do that. Either way, whatever works for you, feel free to do that. And I'll be repeating this one point at the starting of every single lecture in this series, because I really, really want to make sure that you follow this lecture series from start to end so that you maximum benefit from it. So with that being said, let's get into today's lecture and just briefly mention what exactly can you expect to learn by the end of today's lecture. So you will learn about pre-trained embeddings. So pre-trained embeddings meaning if you have a deep neural network that is already trained on some other data set, not the data set that you are currently trying to train a neural network on, but some other internet data set, can you somehow take those embeddings, meaning those weights and biases and those parameters, and can you transfer that to your current neural network and enhance the neural network's ability to perform classification on the dataset of your interest? So pre-trained embeddings can be kind of imported and that can be used in your current model. And this is also broadly called as transfer learning. This is a very famous term and I absolutely love the way, I don't know who coined this term, but this is an absolutely amazing way to mention it because see, people are training neural networks on all types of data sets. So there is no real need for you to train something on your own. If you really think about ChatGPT, there are fine tunings which you can perform on large language models, right? So there is really no need for you to spend millions of dollars to train a GPT completely from scratch or train any other language model completely from scratch. You could also take some LLMs that people have already trained on extensive internet data set and you could perform fine tuning on that. So we'll be learning about these concepts in today's lecture from the context of neural networks for image classification, especially deep neural networks for image classification. But many of these ideas also have parallels with how you do fine tuning in large language models. So maybe if you are familiar with the space of large language models, these terms are kind of familiar to you. But either way, let's get into the lecture, assuming we are starting as a complete beginner. All right. So why are we learning about transfer learning? In our course, the reason why we are doing this is because for every single thing that we are going to do in the future in computer vision throughout this course, you will be almost always using transfer learning. So I'll give you a brief recap of what we have been trying to do so far in this lecture series so that even if you have not followed some of the lectures before, you can still catch up very easily. So we have this data set called as 5 flowers data set. We have 5 flowers, daisy, dandelion, roses, sunflowers, and tulips. What we want to build is an image classifier, a 5-class classifier that can perform classification on top of this. And there are roughly, I think, a few thousands of these flowers in each category. The exact number I have to check. But basically, the data set is not like 100,000 or a million images. It's not that big. It's probably 2 orders of magnitude smaller than 100,000 flower data set. So this is a relatively small data set, which makes it very difficult for training a neural network completely from scratch and achieve very good accuracy. So if you had a neural network which was performing random classification as if it's a monkey, and this monkey is now picking one of these classes as the flower's predicted class, monkey will be accurate 20% of the times, right? Because it's random classification. Similarly, a very bad neural network in this case can get minimum 20% accuracy. Now, with that, if we compare with respect to that very bad neural network, we did three things. First is we tried linear model. And in this linear model, there was no activation function. So no activation meaning we had a softmax layer to get probability distribution at the end. But other than that, in the main architecture, we had no activation function. So what we did was we took the images, converted the RGB pixels into one single flattened layer, and we had a fully connected connections going from this flattened layer into the final output layer. All right. So this was the linear model, and the accuracy that we had, especially in training, was 40-45%, and test validation was maybe less than that, 30-35%, and loss was on the order of 10 to 20. Then what we did is we added one more hidden layer. This hidden layer had 122 nodes, 128 nodes, and this layer also had a rectified linear unit activation function. Unfortunately, although we were expecting better accuracy in this case, we did not get a better accuracy. We got still somewhat similar accuracy as that of 40-45%. Exact number obviously depends on your the specific hyperparameter or specific random number seed, etc. But this was the range of accuracy. But one surprising thing was that the loss decreased from 10 to 20. The loss decreased to 1 to 2. So this was interesting because so we also had a question here. So if loss decreased by an order of magnitude, how come accuracy did not change? That is because the number of images that this model is classifying accurately is not increasing. It is classifying more or less 40-45% images correctly in the validation dataset or in the training dataset, one of them. But the reason why loss has decreased is because each prediction became more confident. So instead of saying this is 75% DAISY, the second model with 128 nodes started saying this is 95% DAISY. So this confidence reduced the cross entropy loss, right? So that was the logic behind loss reducing by an order of magnitude, but accuracy kind of staying the same. Then what we thought was, okay, this is again not very helpful to have just 128 nodes and ReLU activation function. So what we did was we introduced some regularization techniques to make sure that we can improve the model's performance by eliminating possible overfit. We had noticed that there was some overfitting happening from graphs like this. So in this graph, you can see that training accuracy was keeping on increasing after 5 epochs, but validation accuracy had started to drop after 3 epochs. So this was kind of a sign of overfitting happening in the model. So we thought, okay, let's do regularization. So we did regularization with L2 regularization. We used batch normalization. So dataset mean value was close to 0. Dataset's average, the standard distribution was 1. We introduced dropout. So certain nodes in different layers were switched off at a predefined percentage probability. And we also introduced early stopping so that we will not run the model for many number of epochs. So once the moment the validation accuracy starts to drop, it will look for a few number of iterations. And if the validation accuracy is not improving, the model will stop training. So with this, we were expecting a very good accuracy, but that also did not happen. So accuracy only increased to 40, from 40 to 45%, it increased to 50 to 60%. So these were the results. So accuracy increased up to 60% in training. Validation was like 0.45, 0.5 in that range. So not a tremendous improvement, only slight improvement. But it gave us some hope, right? Some hope that, okay, our from scratch approach may work if we do maybe more comprehensive models or some other things. but we could not achieve what we wanted to achieve, which was like 90-95% accuracy. So this is something that makes us happy, right? In a 5-class classification. So that is the reason why today we realize that we have to use a pre-trained neural network. And this is where transfer learning come into picture. So why do we need a pre-trained model? First of all, training deep neural networks like this from scratch on some images, and from scratch, what does it mean? It means if your weights and biases are initialized randomly, starting with those random weights and biases, getting to meaningful weights and biases which allow you to perform very good classification, that is very difficult, especially if your data set is small. You may need millions of images to perform something like that, which we don't have here. We have only thousands of images. You may need GPUs for running the computation for a long period of time, like weeks of computation or days of computation. We were running our computation for just minutes. And if the data set is small, there is a very high chance that the model will learn the patterns in the training data. So overfitting may happen, but on unseen data set, the model may not do much. So these are the issues with having a deep neural network trained from scratch. In our specific case, this is not even possible. We don't have a very large data set. We could have used a GPU and ran weeks worth of computation with large number of epochs, but that will naturally lead to the third problem, which is risk of overfitting. So there was, in fact, a model called ImageNet model. So this was trained on the ImageNet dataset from 2012, and it also resulted in a competition, right? Eventually, all the new convolutional neural network, deep convolutional neural network models were trying to perform really well in the ImageNet dataset. This ImageNet model in 2012 was trained on 1.2 million images. Compared to this, we have only few thousands of images. So there is almost like a 3 orders of magnitude difference. And this was trained over several days using multiple GPUs. So we don't have that kind of money. We are just running a course, right? So that model architecture looked somewhat like this. There are various versions of the model, but somewhat like this. So the question is, in our case, since we have only thousands of images in the 5 flowers data set, what should we do? Can we realistically expect to get good accuracy like 90-95% by training a model completely from scratch? Meaning starting with random weights and trying to train the weights to get to a good stage. Is it realistic with the kind of resources that we have? And the answer is clearly becoming no. We tried many things. We added deeper neural networks. We added regularization. We added various dropout and then early stopping. We introduced batch normalization. Everything we tried, and we could barely reach 50-55% maximum accuracy. So this is why we are now considering bringing pre-trained embeddings. So what are pre-trained embeddings? There are neural networks that are already trained on data sets like ImageNet. So let me show you what exactly is this ImageNet dataset. So there is a website for ImageNet, and here you can see the description of the ImageNet data. Basically, this is a very legacy dataset. Many people were, really trying hard to get their model to perform on this ImageNet data. So basically, this data set has, if I remember correctly, 1,000 classes or something. Let me check. So yeah, so there are 1,000 classes. Actually, Wikipedia says it's not 1,000 classes. In fact, there are 20,000 categories in which images are present, and more than 14 million hand annotated images, if you can read this. So it's a very big image data set. So if we can find a neural network that is already trained on ImageNet, that neural network would have already learned a lot of patterns in general from images, from visual data. If you ask me what kind of patterns, maybe patterns like flowers have this kind of shape compared to some other objects, or the color patterns or the texture. So there are so many things you can learn, just like how a human learns, right? The more things you see, the more you can identify new objects, just the way how you were growing up when you were a kid. So same thing, ImageNet, although the data set is different from the data set that we are looking at right now, it can give us a good neural network that is already having some knowledge about images in general. So that is the reason why we are now looking at pre-trained embedding. So we'll try to use a neural network that is already trained on some images, not on 5 flowers dataset, but some other dataset. And then we'll try to use those embeddings, meaning the neural network parameters from that neural network. And then we will try to train on top of that with our dataset and see if we can get a very good classification accuracy. All right. So I hope this methodology is very clear to you right now. Let us spend a little bit more time on pre-trained embeddings. What exactly are pre-trained embeddings? So they are representations of features in images that the model has learned. So for example, images have objects, like if it is bunch of animals, it will have animals. If it is set of household objects like cups or a microwave oven or something else, so it'll have entire objects. Sometimes images, if you look at a subsection of the images, it will be just a part of an object, like maybe the ear of a cat or whiskers, or like let's say if it's an image of this remote, maybe just a small section of this. So images can have various objects, parts of objects. These objects can have geometric shapes or random shapes. And inside the shape, there could be textures, depending on what kind of material it is. Edges can have various, some edges may be sharp, some edges may be smooth. So these are all features, and these features are represented by numbers in the neural network layers. A trained neural network on images can have numbers that are a good representative of these features which are already present in the images. Now, if we use a pre-trained neural network, and if we are using that to as a starting point to teach from our 5-flower dataset, then the pre-trained embeddings are already kind of good. It's as if you are either using a newborn kid for teaching something versus a kid who has already learned a lot of things, and maybe a kid who is in like 10th grade or 12th grade or something like that. So that it's exactly like that. So we can reuse the pre-trained features from already existing trained neural networks instead of learning from scratch. So this image is from the book only, from the practical computer vision book. So initially we were trying to create fully connected connections from the flattened layer like this into the final output layer, which was 5 nodes. But this has an issue because all the spatial information is lost. We are treating pixels individually. But in fact, the spatial information in the pixel is so important, right? So we cannot expect a neural network to learn everything, all the features in an image just by converting the image into a flattened layer and just making some fully connected connections into the subsequent layer. So this was the mistake that we were making in the very first linear model. Then we proceeded ahead, and now our approach would be, we will have a pre-trained section. So this is a pre-trained model, all right, where maybe convolution operation has already happened. So the weights of these connections and biases in these connections are already set. Then maybe what we can do is we can, in addition, add like a 5 set of nodes, because we are using this model for 5 class classification. Maybe our specific data set could have had 10 classes. So in that case, we would have used 10 nodes here. So the final layer we will be defining ourselves. And if we want to define some layers before that also we can do. But this part will be already pre-trained. And how will this neural network structure look like? It will depend on which neural network we are using from an already pre-trained set of neural networks available to be downloaded or available to be imported. So this is where transfer learning come into the picture. The name is very intuitive. You are transferring the learning, meaning the neural network has already learned something from somewhere. You are transferring that learning. How do you transfer? You transfer in the form of the values of the neural network parameters like weights and biases. So if you are using a neural network that is already trained on some ImageNet 1000 class classification task, and we are using it for a 5 class classification for our 5 flowers dataset, that is an example of transfer learning. There are 2 types of transfer learning. One is called fixed feature extractor. this one. And fixed feature extractor means we don't change anything about the pre-trained model. Pre-trained model is kept fixed. Its weights and biases, no parameters in the pre-trained model we will be touching. We'll be only changing the features of the extra layers that we are going to define. So basically, we are using the pre-trained model just to extract the features. But then there is also another concept called as fine-tuning, which you may have heard of from the context of large language models. And here we can unfreeze the pre-trained model, meaning the layers in the model are kind of accessible to you so that you can tweak it a little bit. And how do you do that? You do that by performing some sort of training and backpropagation to modify the weights in those layers. And here you may be unfreezing only some top few layers, not the entire layers of the neural network. So that at least some part of that neural network also knows a little bit about the current data set that we are working on. So this is called as fine tuning, and you will see the benefit of each of these approaches, and you will see the final classification accuracy that results from each of this. So there may be a question like, when should you use which? When should you just use feature extraction versus when should you use fine tuning? So feature extraction, as you know, it is just pre-trained model with frozen layers. Only the new head, meaning the final classification layer, if it's a 5-class classification or 10-class classification, only that layer is trained. And this is best to use if your data set is quite small, like maybe a few hundreds of data points, so that just with those few hundreds of data points, there is nothing that you can do to modify the already existing learning of the pre-trained model. So in that case, you can just use the pre-trained model for feature extraction. But if you have a medium-sized data set, in our case, I would call a I would say we have around 5,000 to 10,000 data points perhaps. So it's like a medium-sized data set. So, and the task that we are doing here is different. Whereas in feature extraction, the model should be performing a very similar task as that of the original data set. So imagine original data set was also about flowers. Okay. And, let's say a neural network was trained extensively on some flowers data set, maybe some other flowers data set. Then you want to use pre-trained neural network on your set of flowers. But you have only a small data set. Then in that case, you can just use the pre-trained neural network for feature extraction because it was trained on a similar data set, but maybe a larger data set. Now you want to use that neural network on a smaller data set, maybe hundreds of images, but the task is kind of similar. So then you can use feature extraction. In our case, the neural network is trained on ImageNet or some other data set, which are different from the 5 flowers data set. And our data size is not small. It's kind of medium. There are several thousands of images in our data set. So we can use the pre-trained weights, but we will be partially unfreezing some of the layers so that those layers can be retrained. So those layers at the top can be retrained. So this is the difference between when to use feature extraction versus when to use fine tuning. Now let us implement transfer learning without fine tuning. So we'll be performing fixed transfer learning. So the features will be fixed. We'll be freezing the neural network from further modifications. So what we do is we define the base model to be MobileNet v2. So this is the code. So here base model equal to tensorflow.keras.applications.mobilenet v2. We can check the architecture of MobileNet v2 here. This is a very popular neural network architecture. So there are in fact many blog articles and many other places on internet where it shows the MobileNet v2 architecture. So I think these are too simplistic. Let's see. I think this is a very fairly good representation of MobileNet v2, this one. And I'll be sharing some links to papers that has MobileNet v2 explanation. But basically, it's a very simple neural network model, which is already trained on, and we can define which weights we should select. So here we are defining ImageNet weights, meaning this MobileNet v2 we are using such that the weights are trained on ImageNet. The weights are based on what is trained on ImageNet. Now, input shape is dependent on our application, right? So in our case, we are using 128 by 128 by 3. Initially, in the very first lectures, we were using 224 by 224 by 3. Then later we realized after hyperparameter tuning that even 16 by 16 by 3 was performing really well instead of using such a big image. But I thought instead of using either such a big image or such a small image, we can do something in between. So that's the reason why I picked 128 by 128 by 3. 3 because there is RGB, there are 3 channels. So that is the input shape. So input layer will have that many number of nodes. Then we are removing the classification head. So include top is false. And then weights we are using as the ImageNet weights. All right. So this is the base model. So base model will include, if you were to draw the base model, there will be the input layer of 128 by 128 by 3. Then there will be the rest of the things, part of the MobileNet V2. MobileNet V2. And this is the input layer. Now this whole thing is our base model. Now we'll be modifying this base model based on how many classes we are classifying the data into. This is another piece of code that we will be adding in our training, which is base model dot trainable equal to false. So this is where we are freezing the model, which means the weights will not get modified during the process of training. Weights of what? Weights in these layers will not get changed during the process of training. Then comes the classification head. Classification head meaning to the base model, you are adding 2 more things. So TF TensorFlow.keras.sequential. To this, we are adding the base model. Then after that, we are adding another layer called as global average pooling 2D. And then you have the final classification layer of 5 classes with a softmax activation function. So you will get a probability distribution of which class, in what percentage can you expect this image to be part of, let's say, Daisy or Dandelion or the other three flower categories. So to our base model, we are adding 2 more things. There is a pooling operation, and there is a 5 node for 5 class classification, and there is softmax activation also. So now this is the total final architecture of our neural network. So I have already implemented this in code, but before showing you the results, let me show you the number of parameters that you have. So in MobileNet V2, the output shape that come out of it is something such that you have 2.2 million parameters that are there in MobileNet V2. Then what happens is when we are performing pooling, there are no parameters. We are just performing pooling, and it results in 1280 as the dimension. Then in the next layer, there is a batch normalization. So this batch normalization we have been adding since the lecture where we performed regularization. So batch normalization was one of the steps that we did. So we are continuing to do batch normalization, and there are 5,120 parameters here. And in the final layer, classification layer, it's 5 nodes. So 6,405 will be the number of parameters, number of weight parameters. And how do you get this? You can simply do this. You have fully connected connections going from this layer where batch normalization happens to the next layer, right? Which means 1,280 nodes are connected to 5 nodes in the next layer. So you can do 1280 into 5. But then there are also biases, and number of biases would be same as the number of nodes. So 1280. So you can add it. Not 1280. What was it? 1280. Yeah. So 1280 into 5 plus. Okay, my bad. So biases would be added in the 5 node layer. So 1280 into 5 plus 5. So this will be 6405. So that is the number of parameters 6405 that you see here. And now in this, the total number of trainable parameters in the number of trainable parameters. So the total number of trainable parameters should be 5,100 plus 6,400, which should be something like 11,500 plus. But here you can see that the number of trainable parameters are like 8,900. That is because only part of the batch normalization layer is trainable. And so total parameters would be sum of all of this. 2.2 million plus 5,000 plus 6,000. So total still is close to 2.2 million. Out of this, a majority of them are still not trainable. Why? Because we are freezing the model that we are importing, right? The MobileNet v2. Then we implement this in code. So the only parts where we have to make the change compared to what we have been doing so far is in the definition of the model and also in the base model. So basically we'll define the neural network in this way, and then we can do the training as we have been doing before. And here is the part that you were awaiting most. And this is the accuracy plot. The red one is training, and this is validation. And you can see that training accuracy is reaching like 87%. Validation accuracy is reaching like 83, 82%. Much better than what we have achieved so far with any other model. So already with a pre-trained model, with a simple frozen pre-trained model, and we are only allowing the final layer and the batch normalization layer to be trained. And we are already getting amazing accuracy for our five class classification. This is accuracy. Now let's also check the loss. And you can see that previously the loss that we could achieve least was between 1 to 2. Initially it was 10 to 20 in the linear model. Then we could reduce it to 1 to 2. Now we are at around like 0.4, 0.5. So it has reduced by one more order of magnitude. From 2, it has reduced to, from 20, it has reduced to 2. From 2, it should reduce to 0.2 for one more order of magnitude reduction. But if we run this for more number of epochs, maybe the loss will reduce even further. So clearly there is a very good indication of things becoming much better now because of transfer learning. And let me show you the code where I implemented this. So this is the code where I implement transfer learning without fine tuning. So importing the required libraries, weights and biases I'm using to log the experimental results. If you are not familiar with weights and biases, don't worry. I had published a lecture on how to use weights and biases such that you can log the experimental results in a systematic way. So it will not be lost. It will be stored somewhere and you can access it and plot it. You can do a lot of things. But basically, I'm using a batch size of 8, image size 128, 0.0001 as the learning rate, number of epochs 10. And this code we have already gone through in a lot of detail earlier, but basically defining the image height, classes, image width, number of channels, etc. Then we basically have this function for converting image into training. Reading the image from the CSV file. And CSV file links are over here, trained set.csv and validation evaluation set.csv. And using this, we create the training data and validation data. And then here is the part where we define the base model, and then we define base model is not trainable. Then we have average pooling. Then we have batch normalization. So I think this code was not present in the Miro board node. So maybe you were wondering where this batch normalization came from. It's because we have been doing it since the last lecture where we explored how to minimize overfitting. And then we just do model.compile. So this is where we have the final model. And then we have, this is where the training happened. So train data set we pass, validation data set we pass. And then we call this weights and biases .agent with the sweep ID. Sweep ID is defined up here, over here. And when you are running this sweep ID, it will ask you for an API into the weights and biases. You can just copy paste the weights and biases API. You could easily do all of this without weights and biases. Okay, by the way, if you are not interested in using weights and biases, you can remove all these weights and biases thing and directly give, instead of defining a sweep configuration, you can directly give the batch size as 8 where it is being used. So batch size is used here. So instead of using config.batch size, directly put the batch size value 8 or 16 or whatever you want to use. So wherever you see this config dot, that is where I'm using parameters from the weights and biases sweep configuration. If you don't want to use weights and biases, just remove this and add the number directly here. Very simple. And then you can get your final results. You can get your model shape printed, the architecture, parameters printed, and you can run your model, and all the values will be logged into weights and biases. Okay, excellent. So code part is very straightforward. Not much changes from what we have been doing so far. All right. So now let us move into transfer learning with fine tuning. But before moving into that, just remember this accuracy values. Uh, Training is like 84, 85, 86 percentage. Validation is like 82, 83 percentage. So just remember those numbers. Okay. Now let's see if we are doing fine tuning, what happens. Fine tuning part is fairly straightforward. You will not be freezing the layer which we froze earlier, right? So let's see where that is done in the code. So the shape of the base model is pretty much the same. So you have input shape 128 by 128 by 3. We are not including the classification head because classification head was some multi-class classification would have been part of MobileNet v2. So we don't want that because here we are doing a 5-class classification. Then weights are taken from whatever weights the model got as a result of training on the ImageNet. Then here, actually, we are not freezing. Unfreeze. This should be unfreeze the base model. So we are not freezing it. So base model dot trainable equal to true. So it's trainable. The base model is trainable. This is the main difference. And then we basically do the same thing that we have been doing. And here we will not be using learning rate of 10 to the power minus 5. We'll be using learning rate that we were using. It was 0.0001. So we can use that learning rate. But Adam optimizer is what we'll be using: categorical, sparse categorical, cross entropy, metrics equal to accuracy. So this is the final compiled model with the layers are defined over. Okay, sequential layers are not written here, but in the sequential layers, you will have this base model plus there will be 2D pooling, then plus you will have 5-class classification layer. So that will be the total model architecture. So exactly same as what we discussed before, only changes base model is now trainable. Now let's see what results we get after this. So number of trainable parameters are now almost 2.2 million. So most of the parameters we are now training. There are some non-trainable parameters, mainly because there will be batch normalization in some layers. So not all, it will allow you only to train part of the model parameters. But other than that, if you look at the total number of parameters versus trainable parameters, almost all of the parameters are now going to be trained. Only few parameters will be untrained. In the previous case, it was the opposite. Almost 7,000, 8,000 parameters were just trainable. Remaining 2.2 million parameters were non-trainable. So with this is the accuracy that we get. On one hand, you should be happy that, so this is, by the way, training. You might have already guessed this is training accuracy and this is validation accuracy. So one thing is that the training accuracy here, what we have achieved is 100%. This dots are going through value 1.0. So this is a very happy moment for us in the part of this course. So I personally felt very happy to get 100% training accuracy, although this was not, I did not like to see this. So the reason why the gap is so big is because just notice y-axis is being plotted from 0.5 to 1, not like from 0 to 1. So this gap is a bit exaggerated when you are looking at the plot. But yes, validation accuracy is not the best. It's only 80%. But in some ways, this pre-trained model is better than what we had before. What we had before in the, fine-tuned model. Before we did not have fine-tuning, validation accuracy was like 82, 83%. Training accuracy was like 87, 88%. Now we have 100% as the training accuracy and around 80% as the validation accuracy. Not so bad, I would say. This is very, very interesting, but I'm pretty sure some kind of overfitting will happen. If we run for more epochs, this validation accuracy will probably start coming down. I'm not fully sure. We have to run the epochs to see. But let's also look at the loss. This is the validation loss and this is the training loss. And you can see that training loss has reached very close to zero because all the close to zero because all the images are now getting classified correctly. and validation loss is like 0.6. So still much, it's not exactly an order of magnitude smaller than what we had earlier, like loss between 1 to 2. It's but maybe 5 times smaller, or 3 times smaller than what we had. So it's still pretty good. So definitely transfer learning with with fine tuning is working very well, right? We have achieved 100% training accuracy. Now all we need to do is like figure out how to make the model better in terms of performance in unseen data. So that is what we'll be exploring next. But other than that, code part is fairly straightforward. I hope there is nothing different here other than denoting this to be false. Sorry, denoting this to be true instead of false. Base model trainable equal to true. That's it. Just one word difference. But this is the transfer learning with fine tuning. So if you have been following this lecture series, you should be already happy with what you have right now. But let's do two more things to make our training process better. We are keeping constant validation accuracy, like 0.001, 0.0001. So why should we keep the learning rate constant? Why can't we keep it dynamic? Maybe initially the learning rate could be faster. Maybe later we can make it a bit smaller so that finer learning can happen later, right? So that is exactly what we are going to do now, sort of like having learning rate a bit changing as a function of epoch. So two things that we do is, one is we define a predefined set of learning rates. So for the first these many set of epochs, or for these many iterations, you will keep certain learning rate and you will allow it to decay so that learning rate becomes smaller and smaller and smaller. That is one thing you can do. Another thing which you can do is you can define two different learning rates for your base layer and for your head, the head that you define, meaning your pre-trained part of the neural network can have a smaller learning rate because you don't want to modify it that much. It has already learned some features from images from ImageNet. So keep it learning a bit slow. But for the new layers which you are defining extra, make the learning a bit faster, right? Because we don't want too high learning rate. Too high means model will keep oscillating. It won't achieve convergence. Too low means model will perform too slowly. So we want something hybrid. It should be neither too high nor too low. It should also adapt itself. So this is where we try to make transfer learning even better with fine tuning. So it's not without fine tuning. We will do transfer learning with fine tuning, but this time with a different type of learning rate. So here there are a few types of learning rate decays. One is called step decay. So learning rate drops like a step. So here it might be 0.01, then it can become 0.001 after some time. And there is another thing called exponential decay, which is after every epoch, the learning rate will smoothly drop by a fraction. So it will become maybe 90% of what it was before. And then in the next step, it will become 90% of the immediate before step. So like that, it will be going in a certain way. This is called as exponential decay. And then there are many other, like there is something called cosine annealing, in which learning rate will vary like a cosine wave. Initially it will be low, then it becomes high, then again it becomes low, again it becomes high. So these are all various things which you can try. So, but here we will be trying exponential decay. And then we'll also try, which may look like a step decay, but I'll show you what I mean by exponential here. And then we'll also do something called as differential learning. So firstly, learning rate decays. This is what I mean by learning rate decay. In the training, after X number of steps, we say, okay, change the learning rate. Initially, if it is 100 divided by some big number. So this is 100 multiplied by 10 to the minus 6. So 10 to the minus 4, right? This one. Then change the learning rate to 96% of what it was before. Then change it to 96% of what it was in the just before step. So why is this exponential? Because the drop in step size will become decreasing with the time, with number of epochs. Because here the step size is smaller, here the step size is bigger. Because here the drop that is happening is 4%. Here also drop is happening is 4%, but 4% of 95 or 4% of 100 is bigger than 4% of, let's say, 75 or 70, right? So the step size will keep decreasing. That's why it's called as exponential decay. So here we'll be doing that exponential decay learning. So this is just a code for plotting the exponential decay, just for you to visualize it. Now here is how we can, this is actually not step decay, this is exponential. And this is how you can implement it. So you define an initial learning rate. This can be whatever you want it to be, 10 to the minus 4 or 0.0001, whatever it is. And then you say every 100 steps you have to perform the decay. And how much should you decay? You should decay it by 4%, meaning decay rate is 0.96. So if it is 100 initially, it will become 96, then 96% of 96%, like that it will go. So this is the exponential decay function, again defined in Keras. So tensorflow.keras.optimizers.schedule. So this is the learning rate scheduler. Then you define exponential decay. And then all you need to do is, where you define your learning rate, normally you will say this is equal to learning rate equal to 0.0001. Instead of that, you define learning rate equal to this variable LR underscore schedule. That's it. You don't have to make any other change in the code. This is the only change that you need to make. And I will show you the results now. So coding part is fairly simple here, what to change in the code. The results are like this. In the training, we again got 100% accuracy. This blue is training. In validation, we got around 87% accuracy. This is the best that we have ever gotten so far in this course for the five flowers dataset. Of course, we were building from scratch models. We are trying transfer learning for the first time, but I must say this is making me so happy because slowly we are building each concept brick by brick, and now we are getting the fruits of it. So here we know why our model is performing better, because we are transferring some weights, and specifically we are also using a learning rate that decays with time. So initially it learns faster, the model learns faster, later it's slower. Amazing, right? This is simply outstanding. Then if you look at the loss has now decreased. The training loss is close to zero, not exactly zero. Validation loss previously in the immediate thing which we tried before, which was transfer learning with fine tuning, we had a loss of 0.6. Now it is below 0.5. Again, very good, right? So loss has also decreased tremendously. In last lectures, loss was between 1 to 2. So now there is clearly almost an order of magnitude drop in loss. Similarly, in the last lectures, training accuracy, we were barely able to bring it to 50-60%. Now it is 100%. It's so beautiful. Like it's working so perfectly now. Now, the last thing we'll do is implement something called as differential learning rate. The basic idea is this: you have base model, which is pre-trained, and then you have the new classifier head that has a pooling operation plus the 5-class classification, right? The thing is, the pre-trained base model is already knowledgeable. It's like you think of it as a person, this person has already learned a lot from ImageNet dataset. But the new classifier head knows nothing. Its weights are random. So base model need not have a very high learning rate. Its learning rate can be small, whereas the new classifier head should learn a bit fast. So for new layers, use a bigger learning rate. For pre-trained base model, use a smaller learning rate. Because using same learning rate for both parts of the model does not make sense, because it's not optimal logically also. So perform gentle updates for the base model, whereas faster updates, faster learning for the classifier head. And this idea is called as differential learning rate. I implemented differential learning rate. I'll first show you the code and then show you the result. So base learning rate, I in fact defined as 10 to the power minus 5 to keep it small. Head learning rate, I used 0.0001. So this is what I did. So I'm just defining variables here. It's already defined in my sweep configuration, so I don't have to specifically define 0.0001 in this line. Then normally what we do is this. In optimizer, tf.keras.optimizer.atom. Then we say in layers in our model, from the layers till zero meaning layers in the base model, it is trainable, and learning rate is equal to base learning rate. And what is base learning rate? 10 to the power minus 5. Then in the rest of the layers in the model, the learning rate equal to learning rate of the head, and learning rate of the head is equal to 0.0001 or whatever we are defining. So this learning rate is an order of magnitude higher than the base learning rate. So this is how I implemented differential learning rate. The only thing is, after I implemented this, I did not get significantly higher accuracy. Actually, this is the plot that I can show you. Here, my training accuracy reached close to 90%, as you see here. But my validation accuracy was kind of oscillating between 65-70%. So I would say this was around 65%. Maybe this happened because I was not using the best choices of learning rates for both. Maybe that was the reason. So maybe if I do a little bit of hyperparameter tuning, this thing might become better. But I'm just showing you the results from my initial set of experiments. But here, the major takeaway is that transfer learning is such an important thing, because you should not be doing things from scratch if you have a small data set on images and if you want to train a big neural network. So for small data set, transfer learning is so crucial, and you will be doing only this for most of your computer vision tasks. Pre-trained embeddings mean like you are having a person who is already trained. Imagine you are hiring somebody to your company and you have someone who's already trained on a lot of things that your company is doing, which means you get a good head start. You can do tasks better with such a person. Whereas if somebody is a complete fresher, you have to teach them a lot. So that's the main difference between pre-trained embeddings in transfer learning versus normal training neural network from scratch. And fine tuning, we saw, obviously, it improved the model tremendously. We got 100% training accuracy and around, I think, 87, 88% validation accuracy. So that was very good. Then whether we should freeze or whether we should fine tune it depends on your data set. And it depends on the type of task which you are performing. So if your data set is very small and if the task that you are performing is very similar to what the original pre-trained model did, then you can freeze all the layers. But if your data set is somewhat medium sized and if you are performing a completely different task, then you can do fine tuning. So with that, it's a good time to wind up today's lecture. I am very happy at the end of this lecture because accuracy is very good. And once you implement the code, I'm sure you will also feel very good about it. So I highly recommend coding along with me rather than just watching me implement the code or just looking at the results. But in either case, I would like to take a moment to congratulate you for finishing till this part of the course. You have come fairly good distance, looking at starting from the 0th lecture. So 0 to 7, it's been 8 lectures, right? And I would say 1/3 or 1/4 of the course is almost done. So you should feel very good about yourself at this point. I want to congratulate you and thank you for staying with me in this journey. I'll meet you again in another lecture. Take care until then. Bye. See you soon.